Good evening, maybe. I'm going to talk about one of the first results obtained in the framework of an Interreg European project called Optimir, which concern the merging of data sets coming from different mid-infrared spectrometers in the routine analysis of milk. So in the first part, I will just present the project to you, and then I will go more into detail in this topic, and then I will show you the first results obtained. As probably you know much better than I, the northwest of Europe produces more than 60% of the complete European milk production, which means that there is more than 150,000 people employed in this dairy sector and produces a turnover of 70 billions of euros. If you compare to the world cheese here, so you can see that this northwest of Europe produces something like 15% of the total milk in the world, which is quite large if you compare with the main producer, which is Asia or the North America. So for this reason, people coming from this northwest of Europe, they decided to write a project, an European project, and to join all the efforts in order to make what I'm going to present to you now. So this is the Optimir project, which consists of 17 different partners and one subcontracting coming from 6 different countries, so Belgium, France, Germany, UK, Ireland, and Luxembourg. And here you have the participants, so I'm not going to read for you. You have here the milk recording organizations, the research units, and one laboratory from Belgium. Which are the aims of this European project? So the main aim of the project is to improve the profitability and sustainability of the dairy sector, but providing to the milk producers some new, innovative, standardized management tools, which are based on the combination of the spectroscopic information obtained with mid-infrared data and also with some information obtained with the cow's status. With the aim of course, to reduce the cost of production through, for instance, to have an improved daily herd management by reducing the cost of feeding with having some kind of energetic balance indicator, to reduce the veterinary cost, for instance, to be able to have an early diagnostic of mastitis, and also to reduce the cost of semen straws, for instance, to have some kind of insemination equation predictor or something like that. Then also another aim of the project is to bring the opportunities to access to the competitive markets by giving some quality traits, quality related to the higher added value, so something that it was already presented by Marion this afternoon. And also to decrease the impact on the environment by, for instance, to quantifying the methane, which is already done with some other projects. So something that you have to keep in mind with this project is that what we want to do is to consider the mid-infrared of the milk data as a mirror of the cow's status. So what we do, we measure individual milk. We measure milk from individual cows, and then we are trying to relay the information from this mid-infrared spectra that you have seen already in the 2 previous lectures with the fertility, for instance, to determine the pregnancy of the cows, with the feeding of the animal, having an energy balance, with the animal health, as mastitis, as I told you before, and, for instance, to measure the environmental impact by measuring the methane. So how to do that? In order to do that, the people in this project, they decided to merge together in order to create a kind of common transnational database of mid-infrared, but also on all these different parameters that you have here. So here, as the same things as I told you before, and here you have the mid-infrared data. So we want to combine together in this common transnational database in order to play with all this kind of data. So here I'm going just to focus in this part, because it's my part, and this is the part that is in other part of the project. But what happens? If you want to meet infrared data coming from different places, from different laboratories, from different countries, so you have something like this. So you have different instruments coming from different brands, different areas, etc. And you want just to have a common database, you need to do something, because the different instruments, if you're working on that, you know that they are working in different ways. So you need to do what we call the standardization procedures. Because, not only because the instruments are different from different brands or whatever, but also one instrument can change during time or can change due to the conditions of the labs. So, how to perform these kind of standardization techniques? So you have to create some kind of new terms that I'm going to present here. That is a master and a slave. So it means that you have to consider an instrument as a master. And then you have the rest of the instruments that will be considered as slaves of that master. So it means that you are going to transform the data coming from the slaves as if they were measured by the master. This is what we want to do here. So for each slave that I have, I'm going to construct a calibration equation, a standardization equation between each slave and the master. So this equation will be unique for that slave, and it will be used in the future for that slave. In order to perform this step, you need to have some common spectra from the different instruments. So what we do, we send some data, some milk data to the different labs, to the different slaves, and all of them, they measure exactly the same samples. So then I can combine together, and then we can make the standardization. And then, once I have these standardization parameters that I will show you now how to do that, you can apply it for any kind of new samples coming from the different slaves. So how many standardization procedures you can have? A lot. So in the literature, in the infrared, in the near infrared area, this has been applied already for years. In the mid infrared, it's quite new. And you have a lot of chemometric techniques that they are dealing with this. So you can just base in techniques that they are just removing the differences that they can appear in the spectra. So you have techniques as orthogonal signal correction or something like that, that they just try to reduce what is not correlated between the two spectra. But I'm not going to that part. I'm just going to try a transformation that tries to map spectra coming from the slave to the master. And this is the technique that I'm going to present, is the pieceways direct standardization. So this technique, as I told you, so we are trying to transform data coming from a slave as if it was measured by the master. So this technique is based on the fact that the spectral information contained in a certain wavelength in the master is highly correlated to the information that is around that wavelength, in a range around that wavelength in the slave instrument. So I will show you now a figure and you will see it better. So here I have my master, and here I have my slave. So I take a certain wavelength for my master, and I try to correlate this information with a window around that wavelength in the slave instrument. And this will be done just by a classical linear regression model. Here in another way, so here you have the whole spectra from the master and the whole spectra of the slave. So, and this is a moving window method. So it means I'm going to do it for one wavelength. I'm going to calculate all the area around this wavelength in the slave. I'm going to make a regression calibration, can be done by PLS or PCR or any funny method that you can find. And this window will be moved all the time, and then all the spectra will be corrected. So because I was expected you to be very tired, I removed all the mathematics here. So just to tell you that it's a linear regression that I'm doing here, okay? So here it's just a classical linear regression between your master and your slave. So you determine just the different B coefficients of the model and the offset. So here, again, in another way, funny way to do it, so just do this wavelength by wavelength, you determine all these B coefficients, all the offset values, and then when you have a new sample, an unknown spectra that you want to standardize, you just apply the different coefficients that you have obtained. And this is done for every slave of the project, okay? So I'm going to show you some results because it's the most interesting part. So here are the optimal results of quite recent of February and March of 2012. So for this part of the work, we had 25 laboratories with 50 different instruments. And in total, we had received 600 samples or something. What we have done, we have created a complete protocol for the people to be sure that everyone is doing the same, they are working in the same conditions as we are working with the master or with the different instruments to be sure that all the conditions are fulfilled the same. The master that has been selected is a FOSS master that is in Belgium. This is what people received. So people received 9 different samples. These 9 different samples of raw milk contain different, as you can see here, different nitrogen content, so it means protein content, and different fat content. So we created a kind of different set of samples with different concentrations of protein and fat, which is mainly the main content of milk. And then people, they also receive a sucrose sample and a standard sample that it's a kind of detergent or something like that. And this is just to be sure that everyone, the instrument, the slave instrument is stable on time. Because, for instance, sucrose is something that the peaks appears always in the same place. So people, they have to be sure that they have always the same peak. In that case, we are sure that the instrument is not moving. And here you have some of the results. So here are the results for February. So it means that the people, they receive the milk, they measure with the different instruments, and they send back to us the spectra. So with the spectra that I received from the master and I received from the 50 different slaves, we constructed 50 different equations. And these are the equations for February. So the equations according to the master FOSS. Here you have few laboratories from France, from Germany, from I don't know where, and you can see that most of the instruments are FOSS, but you have also some Bentley instruments, and you have also some Delta instruments. And here you have, I represent the results in terms of the slope. So here you have the slope between the prediction done by the master and the prediction done by each of the slaves. And as you can see in red is the prediction before the transformation, and in blue, the slope of the prediction after standardization. Okay? So as you can see, in all the cases, the slope, of course, decreases. So it means that the slave and the master are almost the same. In terms of bias, it's actually the same. So the bias becomes 0 at the end, which is logical. So, but before, and you can see which samples are these, are of course the Bentley, because are the most different from the FOSS instrument, which is the master, and also the Delta, okay? Maybe more interesting topic is the root mean square. So it means is how the model is predicting. So here we are just predicting, I think it's just fat content. So it's a model of fat. So the root mean square error between the predicted value done by the master and the predicted value done by each of the slaves. And here you can see that the error also decreases a lot. So the error is becoming on the same level as if it was done by the master. Okay? And now, even more interesting. So now, in the previous one, here is the parameters done in February. But now, we sent again a new set of samples in March. So people, they measure all the samples in March, and we just apply the coefficients of February to the samples of March. And here is what you have. So you have that the error becomes in the same level as the one of the master also. So in red before and in blue after. Here you have less instruments because we just selected some of them, okay? But just you can see that, for instance, in the case of the Bentley, the reduction it becomes quite impressive. So just to see how it works, this PDS, and how we are playing with the data, this is some kind of example of spectra that we received. So here you have in blue, you have the master coming from FOSS. And in red, you have the slave, one of the slaves coming from Bentley. I took a Bentley because it's one of the most different. The first thing that you can see is that the FOSS has 1,060 different wavelengths, so it's a long range. It's longer than the range measured by the Bentley. The Bentley is 889. And also you can see that, for instance, the FOSS is measuring transmittance, and the Bentley has been measuring absorbance, because the laboratory decided to do like that, even if it was written in the protocol. But you have to take into account all these different things. So because you have these differences in the range, the first step you have to do is just to interpolate to be sure that you are working in the same range. So the first step is just make a simple linear interpolation. Okay? Now, the second step is because I told you we have transmittance and absorbance data. So now, the difference, you know, the Beer-Lambert is just make a logarithm transformation. So then you are already in the same, we are in the same range of wavelength, and then we are in the same conditions. But now, here, you cannot see maybe very well, but you still have a lot of differences. Maybe I can put it bigger. So here you have, before standardization, I still have differences between the different spectra coming from Bentley and different spectra coming from FOSS. And after the standardization, if now I apply my PDS, I get something like that. So now you cannot see any difference between a FOSS instrument or a Bentley instrument, okay? So you have something like that. So now you can be sure that what you are measuring is exactly the same as in the FOSS. Of course, you have all this part that you didn't have in the Bentley instrument. That's a kind of noise. It's just noise of the instrument. It's just due maybe to the water content of the CO2 or whatever, I don't know. So that's the reason that here you cannot modelize the noise. It's impossible. But when people are constructing equations, this part of the spectra is always cut. It's always removed. So you don't need, because you don't have any chemical information there. The chemical information is here and here. So you don't care about the noise. So just to finish, here you have one equation constructed by the master. It's to predict the fat content. So it's more than 1,000 spectra of mid-infrared of milk with reference values, of course, of fat content. So here you have the model, which is quite good. And here you have the prediction of one delta instrument. And you apply the prediction, you have something like that. So you have an error of almost 0.5. Which is quite high. After PDS, you have like that. So you're becoming almost in the same order as in the master. Okay? So just to conclude, I will say that this technique seems to work quite good. It has been already tested several times already in near-infrared data. It works already for years. But it's the first time it's applied in mid-infrared. And so now we are able to say that all the different instruments, slave instruments that we have, now we have applied the same in the data coming from April. They are giving exactly the same solution as the master. This is one of the most important, at least at the beginning, steps for this European project, Optimir, because then you can be sure that you can just construct one single equation for each property of fertility, of mastitis, or whatever they want to do, and you can apply the same equation for all the different labs. And that's what I said here. So this can be used, of course, in the future as an indicator of the status of the cow. So I just want to thank all the people working in the project, and also, of course, to you for your attention.